Hello, in this video we are going to do a little one-on-one video about Xaos and how to use it to create, in this case, something simple, but we will touch on very complex concepts that you can apply to build a more sophisticated fractal flame if you want. So let's create a FLAM3H node, and it comes with the Sierpinski triangle as a default, and this is built using 3 iterators. And now we are having as a default 500,000 points that we can change here. This is pretty much the density of your fractal flame, and is expressed in number of points. So 1 million, 2 million, 5 million, and so on. And if you didn't follow any of the previous videos about Xaos, where I explain a little bit what Xaos is, to make a recap very quickly, Xaos is a weighted probability game that allows us to move a point across iterator using weights. So for example, if a point falls inside iterator 1, it will execute everything inside this iterator. And then in this case, Xaos will define in which iterator this point will go next. And since those weights, now they are all set to 1, and the weight of each iterator, they are all the same, is 0.5 in this case. It has equal probability to go to either iterator 2 or iterator 3 after iterator 1 executed. And if we are about to set a 10 here, that means a point will get executed by iterator 1, and at the end of execution it will look at this weighted probability, and it will most likely fall into iterator 3 right after, because this weight is very, very high. So to start this little example, we will clear the default setting, and we will create just one iterator for now. And now we're going to add a pi variation, which is the one I prefer to use because it's very recognizable. So they are in alphabetical order. So let's go and get a pi variation. There it is. And here inside the vars tab, we can set some parameter to change its shape. We will leave it at default value for now. And so what we are going to do now, we are using very two powerful concepts now that is crucial to build fractal flame. One is the use of a linear variation to construct your fractal flame, and the other one obviously will be Xaos. So we create a second iterator, and let's increase the number of iterations used to solve this fractal flame to 16 in this case. And now, so let's call this pi, and let's call the second one linear 0, 1. And when you have like a shape in one iterator and a linear in another iterator, the linear in iterator 2 in this case will act as a cloner, or the duplicate node in Houdini. So now we can use this to clone this shape. And so we can go inside the preaffine and offset the linear by a certain amount. In this case, 2 will be exactly an equally spaced shape of the pi. And we can see it's cloning it, and the number of clone is dictated by the number of iteration. So if I set this to 4, it will do 1, 2, 3, and 4. It will stop. And the more iteration and the more clone is allowed, is capable to do. So we will stick with 16 for now while we are working. And we see also that the number of points used to clone this shape is reduced at every iteration. And this is dictated by the weight of this iterator. So if we are increasing the weight of the iterator with the linear, we can see we are distributing those points better across all those clones until we reach the end of our iteration. So if we want to increase this, we will set this to 32, and we will go and we'll keep going over and over and over. So for now, we are gonna just stick with 16 while we are working. And now we can do operation like rotating this and create some sort of a circle, and we can scale this a little bit, and we can create a swirl. which is really, really cool. And again, this is the end. It turned blocky. That's when the fractal flame cross its own minimum. And so if you want to fix that, you can do 32 and we can get more until you reach the new limit. So you have to make some tests and define which one you like to live with. And now let's set the location to this iterator with the linear to 1, so we get some color going on. So now we get this cool shape that is built out of the pi variation in iterator 1, and iterator 2 with the linear is taking care of cloning it using its own transformation. Very, very cool. So now, if we were about to create another iterator with a linear and do the same tricks, we will see that if we offset this, we get some sort of a mess. And the reason why is that is because now all the Xaos value, they are all set to 1. And this means this iterator execute the point, and then the point can go back to either iterator 2, or it can go back to either iterator 1, or it can go back to either on itself. And so this number 2 and this number 3 is pretty much cloning the result of each other over and over and over again. And this is the mess we're gonna get. If we were about to set our mission to create a second spiral, so a second one of those maybe here, we will let to work with Xaos and tell him which iterator will affect which. And so in this case, we don't want this iterator to be cloned by the iterator number 3. So we set on iterator 2, the weight, the Xaos weight of iterator 3, we set it to 0. And on iterator 3, we set the weight for iterator 2 set to 0. So we are sure that this point that gets executed inside this iterator, after this iterator executed, will never send the point to number 2, but it can go to either number 1 or to itself. And in this case, we are getting rid of all the mess. And now here, with iterator 3, so linear 2, now we are able to control our second spiral. And so we can do this, and we are going to increase the weight of this, and we are going to scale this a little bit. Maybe too much. A little less. Perfect, and we're going to set the location to 1, so we give it the same color. And now we get 2 independent spiral. One that we control with iterator number 3, and one that we can control with iterator number 2. And iterator number 1 is pretty much the brush. So the linear pi is pretty much backed through iterator number 2 and iterator number 3. And Xaos define the order pretty much in which one iterator is applied over another. And so now we can do the same trick and clone this entire shape across another iterator. And so we can create another iterator, number 4, and set the location to 1. Actually, no, let's set the speed to 1, so we keep the same color. And now, here is the trick. So iterator number 2 is allowed to go in iterator number 4, and that's correct, because we want this to be cloned by iterator number 4. Iterator number 3 is not allowed to go back to iterator number 2, but is allowed to go inside the new iterator number 4. Iterator number 4 on its own should not go back to either iterator number 2 or iterator number 3. And so now we set this to 0 and this to 0. Perfect. And now we can move this somewhere and somewhere. And we can scale it a little bit. Something like this. Perfect. And now we're gonna give it a little bit more weight. And now we got this iterator that is pretty much cloning the result of those 2. This iterator that is cloning the result of the pi, and this iterator that is cloning the result of the pi as well. And so now we can build a complex shape that are all dependent of each other. And so here we can increase the scale of the pie, and everything is propagated through each other iterator. So let me try to increase this a little more. Perfect. Let's give it a little bit more point. Perfect. And now what you can do is you can still modify iterator number 2 and 3, and they will get, the new transformation will get propagated across all the clones. And the same for iterator 3. Very cool. And iterator 4 will get the result of those two and just apply extra transformation on top of it. And now you can go back to iterator 1 and just change your brush. So pie can become, I don't know, let's say blur, and they are like little dots. Or it can become a bubble. Let's see if we find it. Bubble, and we can add a little bit of pre-blur. So we got maybe even more pre-blur. We got some kind of, let's say, bubble soap or something like that. And you can play until you find something that you like more. So let's stick with one. Maybe just pick one over the other, but you can just play. There is one that is called parabola. Yeah, this one is cool too. And you get those kind of cool shape. And if you apply the post affine, and you can rotate your brush. Yeah. And let's try something more. Let's try a CPO. Let's see if I find it. CPO. Yeah. And let's set this to 5. And let's decrease this and increase this. Yeah. And so now if we increase the number of points, let's say 15 million. Let's make small. Now we got all those tiny clone of each other swirling around, which is really, really cool. And so with a little bit of work, you can play with the rotation and the weight to make them align more. And so from 3 very simple iterator, 4 in this case, you can build something really, really complex, taking advantage of Xaos to build a sophisticated connection between each iterator and a simple pre-affine and post-affine transformation. In this case, a rotation. And if we were about to make something a little bit more artistic, we can add another one. And in this one, we can add a race. Let's find it, race. And now if we go to post-affine, and let's move. This will do some sort of, let's say, lens flare or something like that. And let's set the opacity to 0, so we hide the first one in the iteration, which is the blue one. And let's set this to 0.5. Okay. And let's set something so we get different color. Let's stick with this. And now if we were about to, let's say, 25 million. And let's reduce. Now we got those cool little lens flare that kind of run across every swirl. And plus all those nice swirl inside a swirl inside a swirl, which is really, really cool. And obviously playing with a palette and giving it a different color will be another things to try. So yeah, that's pretty much it. I hope you enjoy it, and thank you very much.